So, hey, last class you missed. Okay. Right. This sheet titled multiple block systems and some more. So, predominantly multiple block systems, and hopefully at the end of these problems on multiple block systems, you should get acquainted with the basic ideas on how to deal with one block over another block with forces applied there, with friction here and not there, and so on and so forth. The ideas are very simple, and these problems would be my mouthpiece towards telling you how to deal with multiple block systems, right? So right then, this was a sheet given to you a long time ago, but left unattended for a while, so might as well be done with it. So the first problem is about, let's say, a block A, which is a 2 kg block, a block B, which is a 4 kg block, and the coefficient of friction between A and B is 0.1. And this surface is smooth, horizontal fixed surface, and a force F is applied. Okay. Let's examine the situation. See, when a small amount of force F is applied, right, the two blocks would go together. They move together with a small low value of acceleration. As you go on increasing the value of F, their common acceleration grows, right? Now, the block on top is unaware of the force F. It's only the lower block which knows the force F, right? What is then the communication between B and A? Yes, one, of course. In the vertical direction, they communicate through a normal force. In the horizontal direction, B applies a frictional force so that A could move in tandem with B, right? So that A and B could have a common acceleration. But then there is a maximum tangential force, frictional force, that B can apply on A or A can apply on B, which is mu times mg in this case. In this case, the normal reaction between B and A is 20 newtons, right? 20 newtons is the normal reaction between B and A to maintain vertical equilibrium. So maximum static friction between B and A is going to be mu into 20, which is 2 newtons, right? So F max between B and A, maximum static friction, is 2 newtons. 20 into 0.1, right? Now, let me remove this. Which means A derives its acceleration. A derives its acceleration out of the frictional force that B applies on A, right? And the maximum frictional force that B can apply on A is 2 newtons. So the maximum acceleration of A resulting out of this friction can be 2 by 2, which is 1 meter per second squared. So maximum acceleration of A under no matter what value of F you apply, no matter what value of capital you apply, the maximum acceleration of A can be 1 meter per second squared. As far as B is concerned, there is no limit to the maximum acceleration, because more the value of capital F, the greater will be the acceleration of the lower block B. And therefore, the maximum common acceleration is 1 meter per second squared. That's the maximum common acceleration, right? And when the acceleration of A and B put together, the maximum common acceleration becomes 1 meter per second squared, the frictional force between B and A will become maximum static, right? That means will become 2 newtons. If the acceleration is less than 1 meter per second squared, the common acceleration, then the frictional force between B and A will be less than 2 newtons, right? Now, in the first place, let me find out the force F, the minimum force F that must be applied, or rather the maximum force F that could be applied so that they could move together, right? So the maximum force F that could be applied so that they could move together would be commensurate with their maximum common acceleration. So maximum F, so that they move together, is 6 into 1, which is 6 newtons, right? Mass 6 kgs into maximum common acceleration of 1 meter per second squared, which is 6 newtons, right? Yes or no? The minimum force F that you must apply so that the system or part of the system would move. Well, first of all, in order that any activity between B and A gets initiated, B must move, right? Because until and unless B moves, there would be no association between B and A. Frictional force will not get invoked, right? Therefore, now in order that B could move, all that it has to overcome is the ground, and the ground is smooth. So anything slightly greater than 0 will cause B to move and A and B to move together with a common acceleration. As I go on increasing capital F, the frictional force between B and A will go on increasing. B will apply on A forward frictional force. On A, it will apply a frictional force. Frictional force acting on A would be rightwards. Frictional force acting on B would be leftwards, right? And the maximum value of F would be 2 newtons. Yes or no? Which means now, if you apply a force, let's say F, which is less than 6 newtons, up to 6 newtons, they move together, right? So if you apply a force F equal to 3 newtons, this is an important number for the system then. If you apply a force F equal to 3 newtons, then you know that the two blocks will move together. Now if I look at the two, so one thing that is guaranteed is that they move together. Now if I look upon A and B as one single entity, then for a force of F equal to 3 newtons, when A and B are one unit, then the frictional force that they exert on each other is an internal force, will not appear in the free body diagram of A plus B or in Newton's second law application on A and B. So A and B, when subject to 3 newtons, the two blocks will have a common acceleration, which would be 3 divided by 6, which is half meter per second squared. Yes or no? Now, when a 6 Newton force is applied on the system, then A and B together have a maximum common acceleration of 1 meter per second squared. And the frictional force between B and A acquires its maximum possible value of 2 newtons, right? Now, if I apply a force F greater than 6 newtons, then frictional force between B and A will not increase any further. The frictional force that B will exert on A will continue to be 2 newtons. The acceleration of A then will continue to be 1 meter per second squared, right? So for any F greater than 6 newtons, the acceleration of A, the upper block, will continue to be 1 meter per second squared. The frictional force between them will remain 2 newtons. Yes or no? But the acceleration of B will depend on the value of capital F. Suppose I apply F equal to 20 newtons, right? Now look at the free body diagram of B. B exerts on A 2 newtons to the right, so A will exert on B 2 newtons frictional force to the left. F is 20 newtons. And this will cause, this is a 4 kg mass, this will cause B an acceleration of 20 minus 2, 18 by 4, which is 4.5 meters per second squared would be the acceleration of B. And what would be the acceleration of A? It will remain 1 meter per second squared. Acceleration of A will remain 1 meter per second squared, etc. Yes or no? So for this system of two blocks, this is an important number. From F equal to 0 to 6 newtons, A and B will move together. Frictional force between B and A will grow from 0 to 2 newtons. right? 0 to 2 newtons. For F greater than 6 newtons, frictional force will remain 2 newtons between B and A will continue to move with 1 meter per second squared, and the acceleration of B will go on increasing commensurate with the value of capital F. Sounds all right? Now, let me look at the next problem. Okay? So gradually, you know, we'll just build it up and you'll realize it's all so simple really. Okay? Can I wipe this off? Problem number 2. Is about A, which is 2 kgs, B, which is 4 kgs, and coefficient of friction between B and A is 0.1, and a force F is applied on A. Right? And this surface is smooth. Let's analyze this system. Now, 20 newtons is the normal reaction between the two. So maximum static friction between the two is going to be 2 newtons. Let me wipe this off. F max stat is 2 newtons. And B will only understand frictional force that A exerts on B to get a common acceleration with A. So the lower block B is driven by friction alone. Unlike the previous case where the upper block was driven by friction, in this case, the lower block is driven by friction. The direction in which friction acts on B is rightwards, so that it could have a common acceleration with A. The direction in which B will exert a frictional force on A would be leftwards. Action-reaction pair, right? Now, look, so what is the maximum value of F that A can exert on B in the rightward direction so that they can move in synchronicity? 2 newtons. And this will govern the maximum possible acceleration of B. So maximum acceleration of B is going to be 2 by 4, which is half a meter per second squared. Yes or no? There is no limit on the maximum acceleration of A. It will go on increasing as you go on increasing capital F. But then the maximum common acceleration would be the maximum acceleration of B. So the maximum force that you could apply so that they move together, the maximum force F that you could apply so that they move together would be commensurate with the maximum common acceleration of a 6 kg mass, which is 6 into 0.5, which is 3 newtons. Right? Yes or no? Now, what is the minimum F so that they move together? It can be just slightly greater than 0. Just slightly greater than 0, they will move together. When F is just slightly greater than 0, they would move together, though with a small value of acceleration. Yes or no? Right? When capital F is very small, then they have a common acceleration, which is capital F divided by 6. You could look upon this as one single lumped mass, one single unit in which friction is internal. The only thing that needs to be overcome is friction from the ground, which is 0. So F slightly greater than, so F min is 0. F min is 0. Anything just slightly greater than 0 will cause them to move together. Now, when capital F varies from 0 to 3 newtons, they move together. Frictional force that they exert on each other varies from 0 to 2 newtons. When capital F becomes 3 newtons, frictional force becomes 2 newtons. The acceleration of the lower block becomes 0.5 meter per second squared. That's also the acceleration of the upper block. Now, when F becomes greater than 3 newtons, what happens to the frictional force between the two? It remains 2 newtons. So what's the acceleration of B? It remains 0.5 meters per second squared. So acceleration of B remains 0.5 meters per second squared. Frictional force remains the same between the two. Now, what about A? What about the acceleration of A? See, this is A. Suppose F is 10 newtons. Suppose F is 10 newtons. Right? Frictional force that B will exert on A would be 2 newtons to the left. Right? The mass of this block is 2 kgs. So which means the net rightward force is 8 by 2. The net acceleration is 4 meters per second squared for A. So the acceleration of A will become 4 meters per second squared, as you can see. 10 minus 2, 8 by 2, which is 4 meters per second squared, right? So again, very simple thing. For this, the magic number is 3 newtons. When capital F varies from 0 to 3 newtons, frictional force between the two varies from 0 to 2 newtons. The lower block is driven by friction alone. Up to F equal to 3 newtons, frictional force between them remains static. At F equal to 3 newtons, it becomes maximum static. The acceleration of the lower block then becomes 0.5 meters per second squared. When F becomes larger than 3 newtons, frictional force remains 2 newtons. The lower block remains 0.5 meters per second squared, accelerates with the value 0.5 meters per second squared. The value of the acceleration of the upper block will depend on capital F. It can go to any value, right? So in this case, the magic number is 3 newtons. 3 newtons, there is slipping that just about commences between A and B. For F equal to 3 newtons, slipping just about commences between A and B. Clear? Okay, let's go further. Can I wipe this off? Now we have another system with slight modification. This is block A with mass 2 kgs, block B mass 4 kgs, capital F applied on the upper block. This is mu equal to 0.2. This is mu equal to 0.1. Okay, let's analyze this system and get past the magic numbers. Right? But so far so good, right? Now the normal reaction between A and B is 20 newtons. So maximum static friction here is going to be 4 newtons, 20 into 0.2, 4 newtons, yes or no? So this is maximum static here is 4 newtons. Now, between B and the ground, what would be the normal reaction? 60 newtons. 60 into 0.1, which is 6 newton, is the maximum static friction between B and the ground. Okay, let's then analyze the system. Okay, again, like before, A understands capital F, but B doesn't understand capital F. B will move at the behest of frictional force that A exerts on B and in the forward direction, yes or no? Right? Now, see, is it possible that B moves and A does not move?
So because when the static frictional force between A and B is 2 newtons.
2 newtons.
Between A and B, sorry, 4 newtons.
Okay, first things first. First things first. What is the, see, think of it without biases, free from biases. What is the maximum frictional force that A can exert on B? 4 newtons. Just look at B alone. Just look at B alone. The maximum frictional force that A can exert on B is 4 newtons. Is it good enough to drive B on the ground? Isn't it? It's not good enough for B to be driven on the ground, because for B to be driven on the ground, a minimum 6 Newton is required, right? So until and unless A can apply on B at least 6 newtons or more, B will not move on the ground. So in this case, Hercules comes and applies a force F equal to 10 to power 10 to power 10 to power 10 newtons. Will B move on the ground? No, because the frictional force will still not exceed 4 newtons. Yes or no? So B will not move at all. B will remain static and fixed. How about it? So B is like a fixed surface. B is like a fixed surface. How about it? Right? Which means now the problem becomes very simple. It's like a fixed surface. This is like a fixed surface. And in order that A could move on this fixed surface, the minimum F that you must apply is 4 newtons. Minimum F that you must apply is 4 newtons so that A can move on a fixed surface. If this was not fixed, then the minimum F for A to move on B wouldn't have been 4 newtons, would have been different. But since this is a fixed surface, the minimum F that you must apply on A so that A could move rightwards is 4 newtons, right? So which means if you applied a force F equal to 0.5 newtons, what would be the acceleration of A? 0. Acceleration of B anyways is always 0 here for this problem, for this situation, right? Is it not? Confused? No? When you apply a force F equal to 4 newtons, then it just about, frictional force just about becomes 4 newtons. When you apply a force F on B, on A equal to 2 newtons, what's the value of frictional force that B exerts on A? 2 newtons. Yes or no? Because A is on now, it's as if it's a fixed surface, pinned permanently, right? So, if you apply a force F equal to 10 newtons on A, if you apply a force F equal to 10 newtons on A, then frictional force on A will become 4 newtons, and to the left, F is 10 newtons, and this is 2 kg mass, so the acceleration of A would be 3 meters per second squared. And what would be the acceleration of B? 0. It will always remain 0. Irrespective of the value of capital F, the acceleration of B will remain 0 at all times. Right? Got me? Right? Shall we proceed then? Let's look at problem number 4. So, these numbers, now you can, once I have given you where the demarcation is, in the given problem, with these numbers you can work out the problems, right? For example, in the given problem, F is 2 newtons, both will have 0 acceleration. Minimum force to make system or part of the system move is 4 newtons in this case. And for F is 2 newtons, both will have 0 acceleration. For F is 6 newtons, the acceleration of this would be 6 minus 4, 2 by 2, 1 meter per second squared, etc. and so on and so forth, right? Okay, let's look at problem number 4. Force applied on the lower block now. Force applied on the lower block. Oh, sorry, I mean, I could have, avoided erasing this. No, there is a reason, I have to erase this frequently, because if I leave it for a long time, then it will require Herculean strength to wipe it off from the board. And it's easier to redraw it than to remove it, because for some reason, the quality of ink that they make nowadays is preposterous. It sticks like crazy. Amazing, So, I would have preferred to erase and redraw than, wipe it off. Okay, same. This is A, which is 2 kg. B, which is 4 kgs, 4 newtons, F max is 4 newtons here, F max here is 6 newtons, and force F is applied on the lower block. Okay. Now, is it possible that B does not move but A moves? Is it possible that B does not move but A moves? It is not possible. Because, no, reason being, no, why would A want to move? See, A is dependent on B. Why would A want to move? If it finds friction between B and A would get invoked if B has a rightward acceleration. If B itself does not accelerate, there is no reason for B to invoke frictional force on A and unnecessarily cause mayhem. Right? It's not done. Right? So it's not possible that B does not move when A moves. So A will move only subsequent to B getting initiated into motion. You know what I'm saying? Now, in order that B has to move, what is its first level of battle would be to combat the ground. It has to combat the ground, and the minimum F so that it could combat the ground is 6 newtons. So anything short of 6 newtons will cause B to not move, will cause A to not move. Right? When capital F is slightly in excess of 6 newtons, say when capital F becomes 6.001 newtons, right? Then A and B move together with a common acceleration 6.001 minus 6 divided by 6 meters per second squared, right? When the difference between F and 6 is small, then A and B will move with a common acceleration. The common acceleration would be small. Now, A is driven by friction alone, right? B will exert on A a frictional force to the right, subsequent to capital F being larger than 6 newtons. When capital F, now, when capital F, so we will talk of the regime F greater than 6 newtons only. Because up to 6 newtons, there would be no activity of any sorts. In excess of 6 newtons, they move together with a common acceleration, right? But not forever. The upper block A is driven by the frictional force F that B will exert on A in the rightward direction so that they can move on friendly terms, right? And the maximum F is 4 newtons. So there is a limit on the maximum acceleration of A. What is the maximum acceleration of A? Maximum value of F divided by 2, which is 2 meters per second squared, right? This then will also be the maximum common acceleration of A and B. This also will be the maximum common acceleration of A and B. Now, let us see what value of F will cause this acceleration. So the maximum F so that they can move together would be about their maximum common acceleration, which is 2 meters per second squared. So that's going to be obtained by F max minus 6 newtons equals 6 into 2. Yes or no? F max minus 6 newtons from the ground would be 6 kgs into maximum common acceleration of 2 meters per second squared. Yes or no? Do you all understand this? Repeat, or are you all right? So this gives me F max equal to 18 newtons. F less than 6 newtons, 0 acceleration for both. When F is slightly in excess of 6 newtons, they move together. When F becomes 18 newtons, the frictional force between A and B will become maximum static friction, and they attain a maximum common acceleration of 2 meters per second squared. That means from F equal to 6 newtons to 18 newtons, they are one single unit. They move together in harmony, right? The frictional force between them grows from 0 to maximum static. the acceleration of the two grows from, common acceleration of the two grows from 0 to 2 meters per second squared. This is the regime. Yes or no, right? Now, when F becomes larger than 18 newtons, what happens to the frictional force acting on A? It remains 4 newtons. So what happens to the acceleration of A? It remains 2 meters per second squared. So for any F greater than 18 newtons, acceleration of A will remain 2 meters per second squared. And now, let's say for F greater than 18 newtons, look at B. B is 4 kgs. Say F is 20 newtons. Ground will exert on B 6 newtons. There is relative motion between A and B. Slipping between A and B will commence for F equal to 18 newtons. Slipping between A and B will commence, right? So then B will exert on A maximum static friction of 4 newtons. Yes or no? So then very clearly the acceleration of B would be 20 minus 10 by 4, which is 2.5 meters per second squared. So F less than 6 newtons, no activity in the system. For F less than 6 newtons, both A and B will have 0 acceleration. But for F varying from 0 to 6 newtons, the frictional force between ground and B grows from 0 to 6 newtons. Right? For F greater than 6 newtons up to 18 newtons, A and B move together with common acceleration. Frictional force drives A. A is driven by friction alone. Frictional force between A and B remains static for F less than 18 newtons. For F equal to 18 newtons, it becomes maximum static. A attains its maximum acceleration 2 meters per second squared, which is also the maximum common acceleration. For F greater than 18 newtons, frictional force acting on A remains 4 newtons. It will move with an acceleration of 2 meters per second squared, whereas the acceleration of B will become, for F greater than 18 newtons, it will be F minus 4 minus 6 divided by 4 would be the acceleration. Clear? Mu between A and B is given to be 0.5 and mu between B and the ground is given to be 0.1, and a force F is applied on the upper block. Let's analyze this system. Okay? Now 20 into 0.5, 10 newtons. Maximum static friction between A and B is 10 newtons. Six into 60 into 0.1, 6 newtons. Maximum static friction between B and the ground is 6 newtons, right? Now, question number 1. Is it possible that A moves and B does not move? Why? Yes, yes. Right. See, if A moves and B remains static, then there is relative motion between A and B. Then there is going to be relative. That means the frictional force between A and B will become 10 newtons. A will then exert on B 10 newtons, which is good enough to overcome 6 newtons. B will therefore move. So if A moves, it's not possible that B does not move. Right? Okay. That's one thing for sure. Next. So for sure, from the word go, they will move together. For a very small value of F, they will move together with a common acceleration. But in order that they could move together, B would have to combat the ground. If you look at A and B together, then the minimum F that must be exerted so that they could move together is like B overcoming 6 newtons from the ground. So F min must be 6 newtons that they could move together. Yes or no? Right? The minimum F so that they could move together is 6 newtons. That's a minimum F so that they could move together. right? Because like I said, it's and of course it's not possible that A does not move and B moves. If A does not move, B will not find a reason to move, right? So for sure they have to move together. So for values of F, initially they have to move together, and the only thing that they have to combat is friction from the ground. It's like one single mass of 6 kgs combating 6 newtons from the ground. So F min is 6 newtons, right? Now the lower block is driven by friction alone, right? 10 newtons is the maximum frictional force that A can exert on B, right? Now this tells me the maximum possible acceleration of B. If B is moving, ground will exert on B a frictional force of 6 newtons, and the maximum frictional force that A can exert on B is 10 newtons. That's the maximum that A can exert on B. This will give me a state of maximum acceleration of B. This will give me a state of maximum acceleration of B. A max, this is 4 kgs, which is 1 meter per second squared, yes or no? 10 minus 6 by 4, that's the maximum acceleration of the lower block. This then will also be the maximum common accelerations of the two blocks. This then will also be the maximum common acceleration of the two blocks, yes or no, right? Now let's obtain the value of F so that the two blocks have a maximum common acceleration. Now for them to have a maximum common acceleration, this is A, this is B, F is applied here, and 6 newtons acts on this to the left, and they have an acceleration of maximum common acceleration of 1 meter per second squared. So look upon this as one single lumped mass. There is no relative motion up to this state. Then we have F minus 6 equals total mass 6 into acceleration 1. That means F equal to 12 newtons. Yes or no? So that's a maximum F so that they could move together. That's a maximum F so that they could move together, right? Minimum F so that the system starts to move is 6 newtons, but the maximum F so that they could move together is 12 newtons. See, as you go on increasing F, there is greater and greater propensity of relative motion commencing between A and B, because friction can support only to a certain extent, beyond which it surrenders, right? So from F equal to 6 newtons to F equal to 12 newtons, A and B move together. Their common acceleration grows from 0 to 1 meter per second squared. The frictional force between the two grows from 0 to 10 newtons. Yes or no? Now, so in this case the magic number is 12 newtons. The magic number is 12 newtons, right? Now beyond F equal to 12 newtons, say on A, say F greater than 12 newtons, say F equal to 15 newtons. What happens to the frictional force between A and B after F equal to 12 newtons? Remains 10 newtons. A will continue to exert on B a rightward 10 newton. B will continue to move with 1 meter per second squared, and so on and so forth. Now, if A exerts on B a rightward frictional force of 10 newtons after F equal to 12 newtons, then B will also exert on A an oppositely directed frictional force which remains constant irrespective of the value of F now, right? So the acceleration of A then would be 5 minus 2, 5 by 2, which is 2.5 meters per second squared would be the acceleration of A. And the acceleration of B will remain 1 meter per second squared. That's a system, right? No, no one will move. No one will move. F min is 6 newtons. See, there are two things. For when I claim that it's not possible that A moves and B does not move. That's not possible. Second, I claim that it's not possible that A does not move and B moves. Because if A does not move, then it will not invoke friction between A and B to have any prospect of B moving, right? So initially they have to move together. So initially it's like a 6 kg mass only. Initially it's like as if it's a single 6 kg mass which has to combat the friction on the ground. And therefore the minimum F required for them to just about move together is 6 newtons. Right? Got me? We did 5th, right? Let's look at 6. Mu between A and B is given to be 0.5. Mu between B and C is given to be 0.2. And this is smooth surface. And a force F is applied on the block B, middle block. Let's analyze this system. Okay. 10 newtons is the normal reaction between the two. So the max, so F max would be 10 into 0.5, which is 5 newtons. Right? F max at the AB interface is 5 newtons, yes or no? Now normal reaction between B and C is what? 30 newtons. And therefore F max would be 30 into 0.2, which is 6 newtons. Blocks A and C are driven by friction alone. Right? Blocks A and C are driven by friction alone. When you attempt to move B, B will exert on A a frictional force on A to the right, whose value cannot exceed 5 newtons, and B will exert on C a frictional force to the right, whose value cannot exceed 6 newtons. Therefore, there is limitation on the maximum accelerations of A and C. Maximum acceleration on A would be a situation where B exerts on A maximum frictional force of 5 newtons. That will govern the maximum acceleration of A, right? So the maximum acceleration of A would be 5 meters per second squared. Now, C is driven by friction alone. Maximum frictional force that B can exert on C is rightward 6 newtons. So that tells me the story of the maximum acceleration of C, which would be 6 by 2, which is 3 meters per second squared. Now, which means the maximum common acceleration of A, B and C is going to be 3 meters per second squared. Yes or no? Right? A plus B plus C, maximum common acceleration is 3 meters per second squared, right? Oh, see, what's the normal reaction between B and C? 30 newtons, isn't it? So 30 into 0.2. No? Do you understand why the normal reaction between B and C is 30 newtons? 3 kgs, 30 being balanced by normal reaction that C exerts on B and A together, which is, it exerts an upward 3 kg weight force, right? Now, let us look at what will cause. So a certain value of F will cause the 3 to move together. When I apply a very small value of F, capital F, small f, right? Then the 3 will move together. And the minimum force, minimum F, so that the 3 move together is how much in this case? 0. 0, 0, 0. Minimum F so that the three move together is 0, slightly in excess of 0. Say when F is very close to 0, say 10 to power minus 20 newtons. They move together with an acceleration F divided by 5 is the common acceleration. If it's 10 to power minus 20 whole to power 5, 10 to power minus 100, then they will move with a common acceleration 10 to power minus 100 by 5. So F slightly greater than 0, they will move together. So minimum F so that they could move together is, in a limiting sense, 0. Right? Just slightly in addition to 0, if you apply a force, the three will move together with a common acceleration. Right? As you go on increasing capital F, their common acceleration will keep growing. Right? And the first one to give in would be the block C. When their common acceleration becomes 3 meters per second squared, slipping between B and C will commence. That will happen for a certain value of F. Right? So, slipping between B and C commences. First, slipping between B and C commences first, and this happens for a value of F such that the three have a common acceleration of 3 meters per second squared. That means 5 into 3, 15 newtons. At F equal to 15 newtons, C will part ways because the frictional force between B and C subsequently would not be good enough to support common accelerations larger than 3 meters per second squared. Yes or no? Right? Now, A and B are still carrying the journey of life together for a little while. Beyond 3 meters per second squared, if I go on increasing capital F, then the common acceleration of A and B will become 5 meters per second squared after a while. And at that point of time, A gets a little emotional about things. It says, time for me to part ways. Because frictional force between B and A would have attained its maximum possible value, and A would give in. A would say, all right, I would now continue to maintain 5 meters per second squared. B, alone, all alone. Right? So there is a magic number for slipping to occur between A and B. Right? Beyond F equal to 15 newtons, what happens to the acceleration of C? It remains 3 meters per second squared. What happens to the frictional force that B exerts on C? It remains 6 newtons. From F equal to 0 to 15 newtons, A and B, A, B, C move together like good friends. Right? Their acceleration grows from 0 to 3 meters per second squared. Frictional force between B and C grows from 0 to 6 newtons. Right? So this is one state. One state, F equal to 15 newtons is one demarcation point. Okay? The second demarcation point would be commencement of slipping between A and B, and that happens when they acquire a common acceleration of 5 meters per second squared. Right? So, say for F greater than 15 newtons, A and B move together for a while. Right? Until their common acceleration becomes 5 meters per second squared. Now, how much beyond 15 newtons? So, look at A and B. A, this is B. Their common acceleration becomes 5 meters per second squared. F is the force that you want to apply on B so that they acquire a common acceleration of 5 meters per second squared. C will exert on B a leftward 6 newtons. C will exert on B a leftward 6 newtons. This is the free body diagram of A plus B. So the effect of C will get incorporated in terms of the force that C will apply on B this point onwards. Yes or no? 6 newtons. Right? Now, let's see what value of F will cause this. F minus 6. Mass of A and B is 3. 3 into 5. Yes or no? I hope you realize whatever I have done here. F minus 6, total mass 3 into 5, which is 15 newtons. So this gives me F equal to 21 newtons. When F becomes 21 newtons, the frictional force between B and A acquires its maximum value of 5 newtons, they acquire a maximum common acceleration of 5 meters per second squared, and A is about to leave the party, right? Right? When F becomes larger than 21 newtons, what happens to the acceleration of A? Remains the same, 5 meters. What happens to the frictional force between B and A? Remains 5 newtons. What happens to the acceleration of C? Remains 3 meters per second squared. That is from 15 newtons onwards. From 15 newtons onwards, what happens to the frictional force between B and C? Remains 6 newtons. Yes or no? Right? Now, so there are two magic numbers here. 15 newtons slipping between B and C will commence. F equal to 21 newtons slipping between A and B will commence. Right? For F greater than 21 newtons, acceleration of A will remain 5 meters per second squared. Acceleration of C will remain 3 meters per second squared. But what about the acceleration of B? Say for F greater than 21 newtons, which is the third regime. Look at the free body diagram of B, which is 2 kgs. Frictional force that B will exert on C, B will exert on A from 21 newton onwards would be 5 newtons. So A will exert on B an opposite, 5 newtons to the left. C will exert on B an opposite, 6 newtons to the left. Because B will exert on C 6 newtons to the right, C will exert on B 6 newtons to the left. And F is the force that I apply on B. Then the acceleration of B for F greater than 21 newtons is going to be F minus 11 by 2 meters per second squared. Right? Sounds good? Okay. Mu is 0.1, which means maximum static friction between the two is going to be 1 Newton. Now 20 newtons is the normal reaction between B and C. 20 newtons, yes or no? Right? 20 into 0.4, which is 8 newtons. Yes or no? Then this would be 3 into 0.2 into 10, which is 6 newtons. This is the state, right? All right, let's then build it up. A is driven by friction alone. C is driven by friction alone. So blocks that are driven by friction alone would have a maximum limit of their accelerations, upper limit of their accelerations. Maximum acceleration of A. Maximum acceleration of A would be 1 meter per second squared. Now on B, on C, maximum acceleration would occur when B exerts a maximum frictional force 8 newtons. And if C is moving, obviously ground will exert on it 6 newtons. Therefore, the maximum acceleration of this block is, as you can see, 2 meters per second squared is the maximum acceleration of block C. Okay. Maximum common acceleration of the system 1 meter per second squared. Huh? They will not move together.
Sir, if common acceleration is 1 meter per second square, then common maximum force is 3 newtons.
No, there is frictional force from the ground, F minus 6. So, see, they would move together A plus B plus C for a while, For a while they will move together. But is it possible that B moves and C does not move? No, because if B moves and C does not move, B will exert on C 8 newtons to the right and will cause C to move. So it's not possible that B moves and C does not move, right? Which means from the word go, they are supposed to be moving together. They're supposed to be moving together. Now, the only thing then together that they have to combat as one single unit is frictional force between C and the ground. So, F in excess of 6 newtons will cause the three to move together. If F is, say, if capital F is, say, 6.0001, then the common acceleration of the 3 is going to be 6.0001 minus 6 divided by 3 would be the common acceleration. It will have a small value, right? So for F, capital F, less than 6 newtons, for capital F, less than 6 newtons, don't expect any part of the system to be moving, right? Because if at all, B has to move. And if B moves and say C does not move, it means relative motion between B and C, 8 Newton force that B exerts on C, which is good enough for C to move. So it's not possible that B moves and C does not move. So initially they have to move together. Now there are two weak areas, the AB interface and the BC interface. There would be slipping that would commence between A and B at some time. There would be slipping that would commence between B and C at some time. Which is more vulnerable? AB interface. The AB interface is more vulnerable because slipping would commence between A and B when the common acceleration becomes 1 meter per second squared. So when the common acceleration becomes 1 meter per second squared, A and B will part ways. And B and C will move together for a little while for increasing values of F. But then, for a maximum common acceleration of 2 meters per second squared, C will also have to part ways, right? And then C will continue to move with 2 meters per second squared. The acceleration of B will go on increasing. More the value of capital F, the merrier it gets for B. So, the AB interface and the BC interface. The first slipping will occur between A and B for a maximum common acceleration of 1 meter per second squared. And do you realize this will be 6 newtons, right? So then for AB slipping to commence between A and B, we must have F minus 6 causing A, B and C to have an acceleration of 1 meter per second squared. That means 3 kg's mass into 1. That means F becomes 9 newtons. For F equal to 9 newtons, A and B will, slipping between A and B will just about commence, right? When F is less than 6 newtons, nothing moves. From F equal to 6 newtons to 9 newtons, the 3 move together. Their common acceleration grows from 0 to 1 meter per second squared. Frictional force between B and A grows from 0 to 1 newton, right? Now, F greater than 9 newtons. Acceleration of A remains 1 meter per second squared. Frictional force between A and B will remain 1 newton, right? Now, B and C. Let's see. So F equal to 9 is one magic number. There is a magic number for B and C now. So for F greater than 9, A will exert on B a leftward frictional force. A will exert on B a leftward frictional force of 1 newton, right? And I analyze B and C together. This is 6 newtons frictional force that the ground exerts on C and capital F applied on B, right? They will move together not forever. They would move together until that point of time where C gets its maximum acceleration of 2 meters per second squared. So they would move together up to this state, up to a common acceleration of 2 meters per second squared, right? And very clearly, this state is like F minus 6 is total mass 2 kgs into 2. F minus 7, right? It's minus 6 minus 1 is 2 into 2, 4. 2 meters per second squared, 2 kgs mass, right? So F equal to 11 newtons. The BC interface would begin to split, right? So two numbers here. At 9 newtons, the AB interface would rupture. At F equal to 11 newtons, the BC interface would rupture. For F greater than 11 newtons, what would be the acceleration of A? What would be the acceleration of C? 2 meters per second squared. And the acceleration of B would be F minus 1 minus 8 divided by 1. So for F greater than 11 newtons, the acceleration of B is going to be F minus 9 divided by its mass. These many meters per second squared. I hope why 9. I hope you understand why 9. 1 Newton from A and 8 newtons from C. Right? This, in brief, is the story of multiple block systems. Essentially, you would have to identify vulnerabilities at various interfaces based on which of the blocks is driven by friction alone, which will have its upper limit of acceleration, and proceed with the problem commensurate. Now, whether it's 2 blocks or 3 blocks or 4 blocks, force applied on one or the other, and so on and so forth, the basic idea remains same and it works. Clear? So there is a plank here resting on a horizontal smooth surface and a block mass m at one end. This is smooth. This mass is 2m. There is a force applied on the lower block, which is F is kT. Between the upper and the lower block, let me call it A, let me call this B. Coefficient of static friction is given to be mu, whereas coefficient of kinetic friction between A and B is given to be mu by 2. That's given. This is the data given in the problem, right? Coefficient of static friction, mu, coefficient of kinetic friction, mu by 2. Very unreasonable data. They don't, I mean, they are not in the ratio 1:2, static friction, kinetic friction. You know, they differ by a very small amount, but that's all right for the sake of a hypothetical problem. Okay. Now, this force is applied. The upper block will be driven by friction alone, right? The limit on the upper acceleration of A would be determined by the maximum static friction that B will exert on A, right? So you would expect A and B not to maintain harmony all the time. At some point of time, for a large value of capital A, F, large value of A of acceleration of B, that means a large value of capital F, there would be propensity of A to slide over B, because friction would then have acquired its maximum possible value, right? Now it is given that at t equal to t naught, it is given that at t equal to t naught, A just about begins to slide on B. That means frictional force between A and B would have become its maximum static, which is mu s mg, right? That means at t equal to t naught, at t equal to t naught, the frictional force between the two would have become its maximum, and that would be mu mg, right? Would have been mu mg. Now, so at t equal to t naught, what is the force? F is kt naught. What is the acceleration of the system? F divided by 3m. F divided by 3m. Up to this point, they will move together, right? Up to t equal to t naught, they would move together. So at t equal to t naught, their common acceleration becomes kt naught by 3m. This acceleration is supported by this friction. the friction that B exerts on A at this instant will be mu mg, maximum static, and will support this acceleration of A. That means acceleration of A is that amount A, small a, which would be m into kt naught by 3m. Yes or no? What do you say? At t equal to t naught, A is on the verge of sliding over B. That means friction would have reached its maximum static value mu mg, right? Now at t equal to t naught, they are still precariously moving with a common acceleration. What is their common acceleration? Kt naught by total mass 3m. And who provides A this acceleration? Frictional force. So this frictional force provides A this kind of an acceleration, which is what it is. This is, right? This is the cause and this is the effect. Right? Which gives us kt naught as 3 mu mg. Right? Yes or no? Now let me remove the clutter from you. T greater than T naught. T greater than T naught, A will slide over B. For T greater than T naught, A begins to slide over B. AB interface, there is slipping. AB interface, there is slipping. Clear? And if there is slipping, frictional force now will not be maximum static, it's going to be kinetic, right? So the frictional force between the two is going to be kinetic friction, which is going to be mu k into mg. Mu k into mg, which is going to be mu by 2 into mg. Yes or no? Right? Now at this for t greater than t naught, if I look at block B, lower block, the free body diagram, F is kt, t greater than t naught. B exerts on A frictional force mu by 2 mg to the right, because A is driven by friction alone. So B will oblige A by exerting on it a frictional force Fk to the right, kinetic friction. So A will exert on B Fk to the left. Right? So acceleration of B for t greater than t naught, this is the state after t greater than t naught. Acceleration of B then is going to be kt minus mu by 2 mg divided by 2m. That's the acceleration of B. Yes or no? Kt minus mu by 2 mg divided by the total mass, that's the acceleration of B. What about the acceleration of A? Mu g by 2. This is the frictional force acting on A. See, A now, from this t greater than t naught, A is being A will experience a frictional force mu by 2 mg to the right. Isn't it? Frictional force that B exerts on A is going to be mu by 2 mg. So acceleration of A is going to be mu g by 2 to the right. Yes or no? It's going to be mu g by 2 to the right. Right? Now, can I remove this clutter from you? So acceleration of A is mu g by 2 to the right. Acceleration of B is this. The relative acceleration, A rel, of A with respect to B. The relative acceleration of A with respect to B. Because I want to find the time that A slips over B. A leaves B. This length is L. This length is L, length of this, right? A rel is going to be acceleration of A to the right, which is mu g by 2, minus acceleration of B to the right is this, which is kt minus mu by 2 mg divided by total mass 2m. This much to the right, or minus of this to the left, or minus of this to the left, this to the right, or minus of this to the left, right? So relative acceleration of A as seen by B would be this much to the right or negative of this to the left. Can I remove this part and work on this algebra? So this is like, first of all, let me just simplify this. This is by 4.5, so 3 by 4. Mu g by 3 mu g by 4 minus kt by 2m, right? Minus kt by 2m. I hope you realize whatever I have done. Mu g by 2 plus mu by 4g. Mu by 4g, half plus 1/4, which is 3 by 4 mu g minus kt by 2m to the right. Or relative acceleration to the left is going to be of B of A with respect to B. Of A with respect to B is going to be kt by 2m minus 3 mu g by 4 to the left. But relative acceleration to the left would be, say, dv rel, rate of change of relative velocity to the left, right? Now, what is it that we want to find here? We want to find the speed of the block at an instant observed from the frame of reference attached to the block. That means VREL. VREL will give me velocity of A in a frame of reference attached to B only, because, right? At t equal to t naught, at t equal to 2t naught, the block separates from the plank. I want to find at t equal to t naught what would be VREL. I want to find at t equal to 2t naught what would be VREL. VREL is what I want to find at t equal to 2t naught. Very simple, because do you realize dVREL is kt by 2m minus 3 mu g by 4 dt? Integrate both sides. At t equal to t naught, relative velocity was 0, right? At t equal to t naught, common acceleration, maximum common acceleration, right? At t equal to 2t naught, VREL becomes, say, VREL. So I want to find this VREL, which is easy to obtain. Yes or no? And wherever t naught comes, you can replace it by 3 mu g, mu mg by k. To eliminate t naught, see, this will be in terms of t naught. To eliminate t naught, replace t naught by 3 mu mg by k if required. Right, Parthu? Are you all fine with this? See, this is a diameter OB. This angle is theta. Obviously, you know, this is radius r, this is radius r. So this will also be theta, and this you would expect is 2 theta, right? Now, this particle A moves in a circle of radius r such that this vector r relative to the point O, right? This is the vector r relative to the point O rotates with constant angular velocity omega. Rotates with constant angular velocity omega. Rate of change of this r, this is r. Rate of change of this r changes in a manner that the angular velocity of this r as seen by O is omega. As seen by O means d theta dt must be omega. It means d theta dt must be omega, yes or no? This is what it means. As seen by O means d theta dt must be omega, right? Now, the angular velocity of A as seen by C. Angular velocity of A as seen by C would be d dt of 2 theta. Yes or no? It would be d dt of 2 theta. Angular velocity of A as seen by O would be d dt of theta. Angular velocity of A as seen by C is going to be d dt of 2 theta, right? Which would be 2 omega. 2 comes out, d theta dt is omega. So the angular velocity of A as seen by C is the angular velocity of A in the circular trajectory, right? Omega, 2 omega, and therefore it will experience a centripetal acceleration. The acceleration of A then would be 2 omega squared into the radius r would be the centripetal acceleration. Yes or no? AC. 2 omega whole squared into r would be the centripetal acceleration, which is 4 omega squared. R is the centripetal acceleration of it. Clear? There is a mass m1 here, mass m3 here, m2, m4. There is a string, this is the ground, and the system is in equilibrium. This is the lower thread, these are two springs, this is a thread, and these are the masses, and there is a string which holds m4 to the ground, so that the whole thing is in equilibrium. The whole thing is in equilibrium. The springs would have had some kind of an extension or compression. Don't even bother about what might have been the states of the springs. Okay. Now what is done is and everything ideal here. This lower thread, this segment is suddenly snapped. The system will now be disarrayed. It will run into loss of equilibrium, right? Because this had a role to play in equilibrium, right? This thread must have exerted a tension force T on M4. Yes or no? Which would have been balanced by other things acting on M4, right? Suddenly, if I snap this thread, then there is going to be T acting on M4 upwards. There is going to be unbalanced T acting on M4 upwards. Yes or no? Do you realize that? Because it was this T, the net upward, that the string was balancing. Now if you cut that out, then this T would be missing and there would be an unbalanced T upwards acting on the mass M4. So the acceleration of M4 all put together is going to be T by M4. The acceleration of M4 then would be T by M4. Yes or no? Yes, right? Okay, so the entire exercise is about finding the tension T here. Which will maintain equilibrium of the system. Then T by M4 would be the acceleration of M4 once you snap the string. Clear? Now think of it. Look upon this entire thing as one single unit. Look upon this as one single unit. Okay? Look upon this as one single unit. And if you want to open it up, then M1, M2, M3, M4 with a spring, M4, right? If I imagine it to be opened up, Mentally imagine it to be opened up. Then on M4 there is going to be T to the right. Then there is going to be M4G to the right. When I open it up, there is going to be like a M4G to the right. These are all external forces. Then Mother Earth will exert on M3. M3G to the right. When I open it up, it's downwards, but it will appear rightwards when I open it up. So that's going to be M3G. Now, on opening up, this is M1G and M2G downwards, but it will appear leftwards on opening up. So there is going to be M1G left, and there is going to be M2G to the left. And the system is in equilibrium. And the system is in equilibrium, yes or no? Right? And therefore, what would guarantee equilibrium is T plus M3 plus M4 into G must take care of M1G plus M2G. Spring forces, tension, etc. would be all internal, right? Will not appear in this equation. If this was my system, and that must be M1 plus M2 into G, right? T then would be this minus this would be T. And T divided by M4 will be the acceleration of M4 on snapping the string. No, it's built into this T. See, this T is determined out of spring forces. So it's built into this T, isn't it? The spring force is built into this T. And I have covered the spring forces to avoid unnecessary computations. Therefore, I included the springs as part of the system to get those matters sorted out internally and not allow them to surface. Right? This is the objective of not isolating springs in one form or the other. Yes, springs will have a role, but it's built into this T. It's built into this T. Clear? So T divided by M4. Now, upwards. Now, it's possible that M1 plus M2G is greater than this, or this could be less than this. Based on that, A could be upwards or downwards. Since we do not know whether M1 plus M2 into G is greater than M3 plus M4 into G, I get the algebraic upward acceleration. I get the algebraic upward acceleration of M4. The sign of that expression will tell me whether it's indeed upwards or downwards.
So, but this might give us T to be upwards. This might give us T to be
Well, no, it would then be about whether the spring is being compressed or elongated. This is how I would look at it. This would be about whether the spring is compressed or elongated. Right, let's look at the next one. Yes, please, your attention. A small particle of mass m is released from rest at the point A. Inside a frictionless fixed hemispherical bowl. Frictionless fixed hemispherical bowl as shown. The graph between the ratio of the magnitudes of centripetal force to normal reaction. See, at any given theta there is going to be a centripetal force and there is going to be a normal reaction that the bowl must exert on this particle. So I want to find that ratio. I want to draw the graph of that ratio versus cos theta. Versus cos theta. This is what I want to be able to do, right? Ratio of centripetal force to normal reaction as a function of cos theta is what I want to find. So at a given theta, say, you remove this, it adds to clutter. At this point when the particle comes, what are the forces acting on it? There is going to be mg downwards, right? And there is going to be normal reaction which would be directed towards O, right? Yes or no? This is the tangential direction. Very clearly, what would be, this angle is 90 minus theta, right? This is 90 minus theta. So this would be theta. This would be theta, right? mg could be resolved as mg cos theta this way along the tangential direction, and mg sin theta along the, like this, right? And the particle would have developed a tangential velocity v. Velocity will always be along the tangent to the trajectory. This is the trajectory. It will always be along the tangent to the trajectory. Now, who's responsible? So it's moving in a circle of radius r, and who's responsible for the required centripetal force here? N minus mg sin theta, right? N minus mg sin theta is mv squared by r, right? That's the centripetal force. And while it descends, loss of potential energy must be gain of kinetic energy. It has lost a height r sin theta. Realize this height is r sin theta. It has lost an elevation, which is r sin theta. Is the elevation lost? Right? So loss of potential energy is going to be what? mg into r sin theta. That must be gain of kinetic energy, which is half mv squared. Right? Yes or no? Obviously then, all that you need to do here is to eliminate things. mg sin theta will be like half mv squared by r. So this mg sin theta I can write as half mv squared by r. Yes or no? mg sin theta here can be replaced by half mv squared by r. So then I get n minus half mv squared by r is mv squared by r. So this gives me n equal to 3 by 2 mv squared by r. mv squared by r is the centripetal force. So centripetal force mv squared by r divided by a normal reaction. It does not depend on theta. Do you realize that? It's not depending on theta. It's a constant and equal to 3 by 2, 2 by 3. Fc by n is 2 by 3. So it will be a straight line as a function of, it's independent of theta, so independent of cos theta. So this ratio as a function of cos theta is going to be a straight line parallel to the horizontal axis. Right? While a particle is being projected, as in a projectile motion, we want to find the power delivered by gravity as a function of time. Power delivered by gravity as a function of time. See, I launch with a velocity u at an angle theta, this projectile. This is u cos theta. This is u sin theta, right? T seconds later, what happens to u cos theta? It remains the same. What happens? This is ux, the horizontal velocity. What's the vertical velocity? T seconds later, u sin theta minus gt is the vertical velocity. And gravity is acting downwards. Okay, so this dot, this is 0. So so the net power would be this dot this, but the angle between these two vectors mg and vy is 180 degrees. So power delivered by mg is simply going to be minus mg into Vy, which is u sine theta minus gt. That's the power delivered by gravity as a function of time. I hope all of you understand this. Which is a linear function of time, which is a linear variation with time. Power versus time is going to be a straight line, as you can see. Right? Bless you. Now, fundamentally, for a full time period when the particle goes from A to B, if it is launched with a velocity u, we understand that it falls with a velocity u. So what is change in kinetic energy? Zero. Hey, zero. Change in kinetic energy is zero. That means there is no, on an average, for a full time period, for a full time of flight, the average power delivered by gravity must be zero. Right? That's why there is no net change of kinetic energy. Power should have resulted in change in kinetic energy. If there is no change in kinetic energy, that means the average power for a full time of flight, capital T, must be zero. Isn't it? The average power must be zero for a capital T. Right? Number 13. Very straightforward, really. There is a force F applied at an angle theta, constant force F applied at an angle theta on a particle of mass m. We want to find the velocity developed by m, after it has traveled a length L. Work energy theorem, yaar. Work done by F is what? F cos theta into L is the work done by F, isn't it? It starts from rest here, and this must be change in kinetic energy, half mv squared minus 0. Work done by F is, see, F sin theta does no work, it's perpendicular to the displacement. Work done by F cos theta is going to be F cos theta into displacement in the direction of F cos theta, and that must be change of kinetic energy. You can find the speed once it has traversed the distance L. Clear? There is a smooth incline. This is 45 degrees. This is h equal to 20 meters. This is a mass m equal to 2 kgs. Starting from rest. And there is an observer here. Moving to the right with a velocity of 20 meters per second. See, very clearly, when it falls to this point, it would have developed a velocity v. V squared would be 2gh. V squared would be 2gh, no friction. So v squared is 2 into 10 into 20. Right? So v that it develops on reaching the horizontal surface as seen by the ground is 20 meters per second. Yes or no? Now, that means this is with respect to the ground frame. Now, in a frame attached to the observer, in a frame attached to the observer, this is v equal to 0. Now, observer's frame. The initial velocity is not 0, but is minus 20 meters per second. UREL initially, right? UREL finally, that is in this state, is 0 meters per second in a frame of reference attached to the observer, right? Now, the change in kinetic energy in this frame of reference, in a frame of reference attached to the observer, the change in kinetic energy as perceived by the observer, that means in a frame of reference attached to this observer, is going to be final kinetic energy, which is 0, minus half mass, which is 2 into 20 squared, which is minus 400 joules, is the change in kinetic energy of this particle in the observer's frame of reference, right? Now, change in kinetic energy in this frame would be work done by various forces in this frame, yes or no, right? That means now everything in a frame of reference attached to the observer, change in kinetic energy is minus 400 joules. So observer's frame, from work energy theorem as applied to the observer frame of reference, work done by gravity is going to be mgh, irrespective of the observer, it's going to be mgh, right? So which is 2 into 10 into 20. That's the work done by gravity. Now, work done by the normal reaction in a frame of reference from the ground frame would have been 0. In the ground frame, work done by normal reaction would have been 0, because normal reaction would have been like this, displacement would be perpendicular. Right? Work done by normal reaction in the ground frame is 0. But in this observer's frame, let's say the work done by normal reaction is Wn. In a frame of reference attached to this observer, in a frame of reference attached to the ground, it would have been shunya. Right? Right? And all of this must be change in kinetic energy with respect to this observer. That means must be minus 400 joules. So, work done by the normal reaction in this frame of reference is going to be minus 800 joules, would be the work done by the normal reaction in a frame of reference attached to this observer. Yes, exactly. It will not seem to be moving like this, right? Its displacement would be inclined. All's good? So there is this frame here, one that has a horizontal acceleration of 20 meters per second squared. There is a block here, and the coefficient of friction between the block and this wall is given to be mu equal to 0.6, is the coefficient of friction between the block and the wall, vertical wall, right? G is 10 meters per second square. Now, we will assume that the block maintains contact with this. Right? It maintains contact with this. So, the wall will exert on the block, or normal reaction R, right? Such that, what's the mass of this block, by the way? 10 kgs, right? And this R must be such that the block and the frame have an acceleration of 20 meters per second squared to the right. Such must be R, right? To maintain contact, they must have a common acceleration along the common normal, right? So 20 meters per second squared must be the effect of R, right? Therefore, very clearly, to give this 10 kg block this acceleration, R must be 200 newtons. R is 200 newtons. Yes, Prince. Now, see, this is the block and this is this frame. This frame is moving to the right with an acceleration of 20 meters per second square. We will assume that the block does not lose contact with the frame. So the block must, if I draw the free body diagram of the block, this 10 kg block, it must have an acceleration of 20 meters per second squared to the right. Where will it get that from? Its 20 meters per second squared would be an effect of the reaction force, normal reaction that the wall exerts on the block in the rightward direction to subscribe an acceleration of 20 meters per second squared on it. Right? So R then must be mass into acceleration, right, which is 200 newtons. Now, so that's a pressing force between the two. That's a pressing force between the block and the wall. R equal to 200. The block will exert 200 newtons on the wall leftwards. The block will exert 200 newtons on the block frame leftwards. Right? Right? Now, maximum static friction between the two. See, there is weight acting downwards, which is 100 newtons. Maximum static friction between the two is going to be mu times R, 120 newtons. Very good. 120 newtons. Yes or no? So, it will not slip because it has to support 100 newtons and it can exert an upward force up to 120 newtons, but will it apply 120 newtons? How much will it apply? 100 newtons. So frictional force is 100 newtons. So there would be no relative motion between the block and the frame. There would be no relative motion between the block and the frame, right? Now, the total contact forces are friction force and normal reaction. So R, which is how much? 200 newtons, and frictional force, which is 100 newtons. These are the two contact forces. The net contact force, F contact, would be root R squared plus F squared, root 200 squared plus 100 squared, which is 100 root 5, 100 root 5 newtons. Right? Now, acceleration of the block, therefore, as seen by a ground observer, will be 20 meters per second squared. Why? Because there is no relative motion between the two. Friction is good enough to support the weight. So A is right. Frictional force, yes, is 100 newtons, true. Contact force, yes, 100 root 5. Contact force between the vertical wall and the block is only electromagnetic in character. Yes. Yes. Frictional force, normal reaction. Remember class 1 on Newton's laws. I told you tension, friction, normal reaction, they are all electromagnetic in character. They are all electromagnetic in character. Tension in strings, friction, normal reaction, they are all electromagnetic in character. Deep down at the molecular level, it arises out of an electromagnetic interaction between these particles. They are all electromagnetic in character. D is right. A, B, C, D, all are correct options. Friction force, normal reaction, tension, they are always electromagnetic in character. This is an elevator. Funny elevator, huh? See, it is moving horizontally as well as vertically. That's all right. In physics, it's allowed. The elevator has an acceleration 2I plus 2j meters per second squared. 2 meters per second squared in the horizontal direction, 2 meters per second squared in the vertical direction, right? That's the acceleration of the elevator along the x and the y axis. And the elevator starts from rest. It starts from rest. There is a 2 kg block. There is a 2 kg block kept on the floor of the elevator. There is a 2 kg block kept on the floor of the elevator. Now, in the first 4 seconds, this is t equal to 0. What happens 4 seconds later? 4 seconds later, that is at t equal to 4. Yeah, please come. The elevator develops a rightward velocity Vx, which is 8 meters per second, 80, u plus 80, and develops a vertical velocity Vy, which is also 8 meters per second. 2 into 4. We will assume that the mass does not lose contact with the elevator. So this is also the kinematic status of this 2 kg block 4 seconds later, right? Yes or no, Prince? Now, there are various forces acting on the 2 kg block. On the 2 kg block, if you think about it, there is normal reaction from the ground, right? There is normal reaction from the ground. There is mg acting downwards, Mother Earth, right? And there is frictional force acting to the right, not in the ground frame, in the ground frame. There is no pseudo force in the ground frame, right? And there is frictional force to the right. These are the 3 forces, right? And the work done by all these forces put together from work energy theorem must be change in kinetic energy, right? Work done by all these forces put together, work done by all forces in the ground frame, because these are velocities in the ground frame, work done by all forces put together in the ground frame is change in kinetic energy, which is half m Vx squared plus Vy squared minus 0 squared, right? So which is half of m into 8 squared plus 8 squared. These many joules, 64 plus 64, that makes it 128 joules, is the work done by all forces put together. Now, work done by friction. Friction is acting to the right. And what's the nature of this friction? Static, because there is no relative motion. And work done by static friction need not be 0. Work done by static friction need not be 0. In this case, what's the work done by static friction? Static friction is acting horizontally. That's the only horizontal force acting rightwards. Therefore, change in kinetic energy in the horizontal direction must be work done by static friction. Yes or no? So, work done by static friction must be change in kinetic energy as seen horizontally, which is going to be half m into 8 squared, right? Which is 64, half of it, 64 joules is the work done by static friction. Now, in the vertical direction, what are the two? And what's the work done by static friction in a frame of reference attached to the elevator? 0. Because displacement with respect to the elevator horizontally is 0. So, work done by static friction in a frame of reference attached to the elevator is going to be 0. Right? So, work done by a force will depend on the frame of reference, right? Work done by normal reaction plus gravity, these are vertical forces, will be change in kinetic energy in the vertical direction. That means half of 2 into 8 squared, which is 64 joules, is the work done by normal reaction plus gravity. Perfect? So option A is right, option B is right, option C is not right. Work done by normal reaction plus gravity is 64 joules. Yes or no? Work done by friction force in the frame of the elevator is 0 is right. See, one thing, so the next problem, but a prelude to that problem, in a typical projectile motion, if u is the velocity and this angle is theta, the maximum height attained is u square sine square theta by 2g. That's the maximum height attained, which is initial vertical velocity squared by 2g. The time of flight is, total time of flight is 2u sine theta by g, which is twice initial vertical velocity by g. Now, if in the horizontal direction there are abnormalities, say there is viscous drag, there is fluid drag, etc., something or the other, causing a force or drag leftwards or rightwards, causing an acceleration a naught, then neither the maximum height will change nor the total time of flight will change, because that depends on only the initial vertical velocity divided by g. That will not change. So h max will remain intact, the total time of flight will remain intact. However, the range of flight will change, because u cos theta into capital T will change. Why isn't it? Because u cos theta will not remain the same. U cos theta will change if there is an acceleration horizontally. So the range will change, the path will no longer be a parabola, but the maximum height for any trajectory obtained will still be uy squared by 2g. The total time of flight will still be this. The particle will not land here, will land somewhere else, right? So horizontal variations will not change two things. The maximum height attained will not change, the total time of flight will change, the range will change the trajectory, right? Now come down to the problem. Can I wipe this off? Paragraph. There is a breeze causing a leftward acceleration of a naught on this particle. There is a breeze causing a leftward acceleration of a naught on this particle. Now, we want to be able to determine a naught. We want to be able to determine a naught such that the trajectory is a straight line. We want to be able to determine a naught such that the trajectory is a straight line. Now, notice, this is the velocity. U naught at the point of projection, this is the velocity. There is a vertical acceleration which is g, like this, and there is a leftward acceleration which is a naught this, right? Now, if the resultant, so the net acceleration of the particle will be the resultant of a naught and g naught. If the resultant of a naught and g naught is from B to A, then the velocity and accelerations are aligned and the particle will move along a straight line. You know what I'm saying? If the resultant of a naught and g, if the resultant of a naught and g is from B to A, then the particle will move along this trajectory only. Yes or no? If the accelerations are and velocities are in the same direction, then the particle has to move along a straight line, right? That means the acceleration, the net acceleration perpendicular to AB must be 0. If the net acceleration is along AB, then the acceleration perpendicular to AB must be 0, yes or no? Right? The net acceleration perpendicular to AB must be 0. Perpendicular to AB must be 0. This is the requirement. The net acceleration perpendicular to AB must be 0, so that the net acceleration is along AB. Right? This is theta. What is this? Theta. This is theta. Right? Now, A naught sine theta is the acceleration perpendicular to AB like this. This is A naught sine theta like this. A naught sine theta, component of acceleration perpendicular to AB. And G cos theta is like this. Right? G cos theta is like this. The net acceleration in this direction must be 0. That means A naught sine theta must be equal to G cos theta. Right? So A naught must be G cot theta. A naught must be G cot theta. Yes or no? Right? So if A naught is G cot theta, particle will move along a straight line. It will go from A to a point C. It will retard, its velocity will become 0, it's launched with a velocity u. It has a net acceleration resultant of A naught and G naught like this, A this way. It will retard, its velocity will become 0 like this, but its acceleration continues to be A like this. So next it will go from C to A with an acceleration A. Yes or no? Right? It will come back to A. Clear? The maximum height, however, like I told you, will not depend on what's happening. This is H max. That's C is the highest point. So this is H max, which, like I told you, no matter what A naught be, will not depend on the horizontal conditions. Right? Will remain u squared sine square theta by 2g. And the time it takes to go from A to C and back to A will still be 2u sine theta by g. Right? Got me? Hello. Yes, please. So far so good, right? An object O, mass m, fixed at point O, attached to a thread of length L, and it's released. It's pivoted at O. This thread is pivoted at O. All right. Now, when it's pivoted at O, you realize O will move in a circle of radius A, centered at A. O will move in a circle of radius L, centered at A. Now, after a while, so this is the trajectory of O. This is the trajectory of O. O prime. Now, after a while, let's say this is an intermediate state of O. This is an intermediate state of O. Right? This is an intermediate state of O. Now, say this intermediate state characterized by theta. Theta runs from pi by 2 to 0. From horizontal to vertical, theta runs from pi by 2 to 0. Right? Now, we want to find the velocity of the object when the vertical component of the velocity is a maximum. So while it's moving along this trajectory, its horizontal and vertical velocities are changing, right? We want to find the velocity of the object during this trajectory when the vertical velocity is the maximum. It could be when the vertical velocity is the maximum. It could be yes or no. That's the objective. Clear? Okay. See, one thing. I want to find the theta. I want to find the theta when vertical velocity is the maximum. Then we'll find the maximum velocity, etc. See, there is mg acting like this, right? There is tension in the string like this. These are the two forces. This is the tangential direction. This is 90 minus theta. This then will be theta. Right? Clear? This is theta. This will be 90 minus theta. With the tangent, it will be theta. Huh? This will be theta. mg you might want to resolve as mg sine theta, or rather leave it like this. The velocity would be this at this instant, right? And at this instant there is a vertical velocity vy and there is a acceleration, a vertical horizontal velocity vx, right? What is it that we want to maximize? We want to maximize Vy. We want to maximize Vy, right? We want to find theta such that Vy is maximum. Now for Vy to be maximum, dVy dt must be 0. But what is dVy dt? Acceleration in the vertical direction. That means at an instant when Vy is Vmax, acceleration in the vertical direction must be 0. This is the physical requirement. This is the physical requirement, yes or no? For Vy to be maximum, dVy dt must be 0, but dVy dt is acceleration in the vertical direction. That means the net acceleration in the vertical direction must be 0 for the particle. Such must be theta. Now, see, there is centripetal acceleration like this. When it comes to this point, there is centripetal acceleration this way. Right? This must be theta. Yes or no? So, what is the net vertical acceleration? mg minus ac cos theta. Sorry, g minus ac cos theta, right? G minus ac cos theta. How do I find ac in this state? I need to know the velocity in this state, right? How do I find ac in this state? V squared by L, V squared by L, yes or no? Now, when the particle goes from this point to this point, when the particle goes from this point to this point, right, what happens? Loss of potential energy must be gain of kinetic energy. This length is L. This length is L. This length will be L cos theta, right? So loss of potential energy is mg into L cos theta, right? And that must be equal to gain of kinetic energy. What is gain of kinetic energy? Half, it starts from rest, half m v squared. V squared therefore would be 2gl cos theta. Now, the tension being T, do you realize T minus mg cos theta is going to be mv squared by L. T minus mg cos theta, the net T minus mg cos theta is mv squared by L. Is mv squared by L? So mv squared by L is 2g cos theta. So this will become 2 mg cos theta. See, I hope all of you realize whatever I've done here. Mv squared by L would be 2 mg cos theta. T then would be 3 mg cos theta. Okay. Suppose I have obtained V. Suppose I have obtained V. Then what's the vertical velocity? V sine theta? V sine theta is the vertical velocity, right? Vertical velocity is V sine theta is the vertical velocity, right? V is root 2gl cos theta into sine theta. Right? V is root 2gl cos theta sine theta, that is, so now Vy is a function of theta. How do you maximize Vy? dVy d theta must be 0, right? Which means root cos theta means 1 by 2 root cos theta, right? 1 by 2 root cos theta to minus sine theta. So minus sine square theta plus cos theta into root cos theta must be 0. Right? This gives me 2 cos square theta is sine square theta. 2 cos square theta is sine square theta, isn't it? I transpose this on this side. So 2 cos square theta is sine square theta. That gives me tan theta equal to root 2. Tan theta equal to root 2, such must be theta, yes or no? Right? So once I know tan theta, then cos theta is known to me. Right? Cos theta, if tan theta is root 2, cos theta would be 1 by root 3. 1 by root 2 squared plus 1. 1 by root 3 would be cos theta. So you can plug in cos theta is 1 by root 3. Cos theta is 1 by root 3 and V could be obtained from these considerations. Yes or no? Yes or no? Right? Put cos theta is 1 by root 3 here and V is known from these considerations. Such must be theta. Right? Yes, vertical acceleration equal to 0. Yes. You could have directly got this by saying vertical acceleration equal to 0. You could have got tan theta equal to root 2 just by saying vertical acceleration is 0 at this point. You would get the same thing. Check that out. Okay. And I want to find the tension at this instant. When cos theta is 1 by root 3, put cos theta is 1 by root 3, you get root 3 mg. That will give you the tension at this instant, and so on and so forth. Right? Ratio of maximum vertical velocity. We know the maximum vertical velocity from these considerations. Right? We know the maximum cos theta is 1 by root 3, we know V max, vertical, V max, and then the corresponding Vy can be obtained from these considerations, and we want to be able to find the maximum vertical velocity, which is this, at, right, divided by the maximum horizontal velocity. When is the horizontal velocity the maximum? When physically, when it reaches a vertical state, when O comes here, then the entire velocity would be horizontal. It will be V max, right? That's going to be a state of maximum horizontal velocity. Yes or no? And V then, that means theta equal to 0, V squared would be 2gl. Isn't it? This would be theta equal to 0 and V squared would be 2gl. That V would be the maximum horizontal velocity. That will be the maximum horizontal velocity. Clear? Number 22. There is a rough rod and there is a bead of mass m. There is a bead of mass m which is constrained to move inside this rod, which is constrained to move along the rod only. The length of the rod L is 30.6 meters. The length of the rod L is 30.6 meters. Now, at the initial moment, the bead is in the middle of the rod. This is L by 2, this is L by 2. The bead is in the middle of the rod, right? The rod moves with a constant acceleration of 5 meters per second squared as shown. The rod is made to move with an acceleration a naught of 5 meters per second squared to the left at an angle 37 degrees. The coefficient of friction between the bead and the rod is given to be mu equal to 0.2. Is given to be 0.2. We want to find, so these are open ends and the bead can escape through the open ends. We want to find the time it takes for the bead to escape the rod. That means traverse half the length of the rod with respect to the rod. Clear? Now, let me look at M in a frame of reference attached to the rod. Let me look at small m in a frame of reference attached to the rod. Then, do you realize that it will experience a pseudo force ma naught? It will experience a pseudo force ma naught like this, right? 37 degrees. Now this ma naught could be resolved as ma naught cos 37 degrees like this and ma naught sin 37 degrees perpendicular. Right? That means this particle will press against the rod. The rod will then exert a normal reaction N on the particle like this. Right? Since there is propensity of this particle to go in this direction, there is going to be frictional force. And by the way, this will give me the relative acceleration of the particle with respect to the rod because it's a pseudo force. So if you deploy the pseudo force, you get the relative acceleration along the rod. So ma naught cos 37 degrees. That means a naught cos 37 degrees would be the, will not be the acceleration, will be part of the acceleration, relative acceleration along the rod. Now, because there is also going to be frictional force. This was the pseudo force ma naught resolved perpendicular and along the rod, and there is going to be frictional force. Now, in this direction, there would be no motion of the rod perpendicular to the rod. There would be no motion of the particle perpendicular to the rod because it's constrained. So what must n be? N must be ma naught sine 37 degrees. Right? What would be frictional force? Mu n. Right? So the net force acting along the rod with respect to the rod in a frame of reference attached to the rod. Why in a frame of reference attached to the rod? Because I have incorporated the pseudo force, right? So the net force along the rod is going to be what? M A naught cos 37 degrees minus mu times n, minus mu times n, minus mu A naught sine 37 degrees. A naught cos 37 degrees minus mu A naught, mu times n, right? Yes or no? And this will give me this divided by m will give me relative acceleration with respect to the rod. Will give me relative acceleration with respect to the rod. Yes or no? Along the rod, this will be relative acceleration along the rod in the rod frame of reference, right? This is like A naught cos 37 degrees is 4 by 5. How much is mu? 0.2 into 3 by 5. A naught is 5. A naught is 5, right? So this A naught will cancel with this 5. 0.6. 3.4. 3.4 meters per second squared is the relative acceleration along the rod, right? Constant acceleration with respect to the rod along the rod. Now, if it takes t seconds to go from this point to this end E, then can I say the relative distance is L by 2? Must be half of ARL, half of 3.4 into t squared. Right? What is L given to be? 30.6. So this will go 9 times. T then will be 3 seconds. T then will be 3 seconds. It takes 3 seconds for it to escape the rod. 3 seconds for it to escape the rod. So, problem number 23 of the previous sheet. There is a smooth, uniform dish plate of mass 2m, uniform dish plate of mass 2m, placed on a smooth horizontal table. Two particles of mass small m each are placed at diametric positions. These two particles are placed at diametric positions and are imparted velocity v each. V is given to be √2 meters per second. Find the speed of the particle before they collide. We want to find the speed of these particles, particle A and particle B, say, just before they collide. All right. Now, yes, in this system, see what's the net linear momentum in this direction? 2mv minus 2mv, 0. So in this direction, there are no forces acting, net forces acting on the system. So linear momentum in this direction must be 0 all the time. Because see, initial momentum is 2mv minus mv, 0, right? So, and again, realize when they collide, just before collision, one particle, so they would collide, let's say at this point P, isn't it? Because of symmetry, they would collide at this point P from symmetry considerations. One would have a velocity v1, the other one would have the same velocity v1, but in the opposite direction. Yes or no, from symmetry considerations. They must collide at this point, and one would have a velocity v1 to the right, the other one would have a velocity v1 to the left. There is no way to distinguish between the two particles, and therefore this. And since these two particles have only horizontal momentum, so they are party to no momentum in this direction, which was 0 all the time. So it should remain 0 at this instant also. So this 2m will have velocity 0. And the net linear momentum horizontally continues to be 0 because it was 0 in this state. It will stay 0, and therefore v1 and v1 like this, to preserve linear momentum 0 in this direction as well, right? Total kinetic energy must be constant. So what's the kinetic energy here? For the mass 2m, half of 2m into v squared plus 2 into half of m into v squared. That's the kinetic energy here, and that must be equal to the kinetic energy, two masses, mv1, mv1. So that must be 2 into half into m into v1 squared. V is known, so you can obtain v1 from these considerations. Total kinetic energy remains constant in this case. Okay. If it didn't move, if it had a non-zero velocity here, then the entire system would have a non-zero linear momentum in this direction. But look at this. What's the linear momentum in this direction? 2mv minus 2mv 0. So if it didn't stop, it will have a non-zero linear momentum in this direction. Right? So there is this frame, box, which is moving up with an acceleration g. Right? And there is an inclined plane here, say at an angle theta equal to 37 degrees. Right? And there is a particle which is projected inside the box with a velocity u at an angle theta equal to 37 degrees. That's given in the problem. Find the radius of curvature in meters of the path followed by the particle with respect to the box when the velocity becomes parallel to the inclined plane in the box frame of reference. That is, everything in the box frame of reference. U is given to be 160 by 7 meters per second. Very simple. Your attention, please. See, I can imagine the box to be fixed and replace g by g plus a. That means g by g, 2g, right? So it's as if that the box is rest, so and g is 2g, right? Now, so now the box is rest, box frame of reference. The particle will undertake a trajectory of this kind, right? And at this point, at the highest point, it will have a velocity v, which would be parallel to the plane in the box frame of reference, right? That means velocity perpendicular to the plane must become 0. If it has a velocity purely in this direction, say this is the x direction, this is the y direction, then the velocity in the y direction must become 0 in a certain time t, and the velocity in the x direction becomes, say, vx, right? So let me find out the time it takes for the velocity in the y direction to become 0, right? Again, you can resolve 2g as 2g cos theta like this and 2g sin theta like this, right? So if I write the equation of motion in the y direction, right, velocity in the y direction in time t becomes 0, is initial velocity in the y direction, which is what, u sin theta, right? U could be resolved as u cos theta like this and u sin theta like this. So velocity at this instant in the y direction becomes 0. Initial velocity in the y direction becomes u sin theta minus 2g cos theta into t, right? Acceleration in the y direction is minus 2g cos theta, right? So minus 2g cos theta into t. So t is known, right? T is what? T is u by 2g tan theta, right? Now in this time, what happens to Vx? In this time, what happens to Vx? Vx then becomes, in this time, initial velocity in the x direction, which is u cos theta, minus 2g sin theta into t. This t you can plug in, u by, isn't it? So 2gt is u tan theta. This 2gt I can write as u tan theta, etc. So Vx is known in this time. Now the radius of curvature at this point P. See, at this point P, the highest point, let's say P, this is Vx. This is 2g. This is 2g cos theta, right? So this is the common normal direction. This is the normal direction at this instant. So radius of curvature would be Vx squared by 2g cos theta would be the radius of curvature, isn't it? Centripetal acceleration is going to be Vx squared by r. If r is the radius of curvature, Vx squared by r would be the centripetal acceleration. And who provides this acceleration? 2g cos theta. So from this, r can be obtained because Vx we have already obtained, and you can obtain r from these considerations. The radius of curvature when the velocity becomes parallel to the inclined plane in the box frame of reference. This is all in the box frame of reference. Got me? Yes, then your attention one more time, one last time for today. So there is a spring here attached to a mass m, and there is a force F applied to this mass m. Initially the spring is vertical and unstretched, L0. It's vertical and unstretched and is of length 3L0. Is of length 3L0. That's the natural length of the spring. A constant force is applied on the block so that the block moves in the direction of the force. When the length of the spring becomes 5L0, so after a while, the spring will acquire this state, the mass m will be here, and the spring will become 5L0. That means the mass would have traversed a distance 4L0. Must have been the distance traversed by the mass. When the length of the string becomes 5L0, the block leaves contact with the table. That means at this instant, the upward spring force just balances the weight, right? So it's on the verge of losing contact with the ground. Also, it's given that the velocity at this instant is 0, the velocity at this instant is 0. I need to be able to find the constant force F. I need to be able to find the constant force F under these conditions. Simple. I'll apply work energy theorem. What's the work done by F? F into 4L0. Right? What's the work done by the spring force? Negative of the change in elastic potential energy. So minus half K into change in length 2L0. 2L0 is the change in length. So elongation is 2L0. Elongation is 2L0. So half K into 2L0 squared is the work done by the spring force, and that must be change in, which is 0. right? That must be the change in kinetic energy, which must be 0. Now, that's not about it. At this point, what is the spring force? Say, this angle is theta, this angle is theta. What is the spring force here? Huh? Yes, K into 2L naught, because the elongation is 2L naught. So the spring force is going to be K into 2L naught. And the vertical component of the spring force, K into 2L naught, must just about take care of the weight, mg. So very clearly, this F into 4L naught, and this is K into 2L naught, cos theta, cos theta, cos theta, right? So K into 2L naught, K into 2L naught is mg by cos theta. So this will become K into 2L naught, which is mg by cos theta. That must be 0. Right? Cos theta is known to us very clearly. Cos theta is 3 by 5. Cos theta is 3 by 5, which you can plug into this and obtain the value of F. Now this K will not be there. K into 2L naught, K into 2L naught is mg by cos theta. This K will get cancelled, right? So mg by cos theta, so F is known from these considerations. Right?